Okay, I think we can get started. Uh, Hi, everyone. Welcome to our second SNAPP seminar this semester. It's our great pleasure to have Professor Zeyu Zheng as our speaker today. Zeyu is an associate professor in the Department of Industrial Engineering and Operations Research at University of California Berkeley. He received his Ph.D. in management science and engineering from Stanford University and his bachelor degree in mathematics from Peking University. He is currently the director of the Berkeley Artificial Intelligence and the Simulation Lab, and he has done very interesting work on generative AI models, experiment design, and non-stationary learning. He is also an expert on simulation, inference, and stochastic optimization. Today, he will talk about his work on non-stationary in A/B test. The floor is yours. Please take it away.
Thank you very much, Qiaoming, for the very kind introduction. I also like to thank Zhang Han and the committee, Daniel, Yu, and Ziva and Mondi for the invitation. It is my great pleasure to present and share this part of the work that we have done. And the topic is on non-stationarities in A/B tests. I will specify the definition of a non-stationarity in after a few slides. But this is a joint work with Yuhang, Guangyu, Zhouhan, Chu, and in particular, I like to highlight Yuhang, who is a PhD student working with me here at Berkeley IUR. And Yuhang has done the majority part of the heavy lifting, the work. Okay. And here is a brief outline of my plan for today's presentation. I'll start with a brief review of A/B tests. I know many of the audience are very knowledgeable about that, but for completeness and also really more for the notation-wise, I like to use this brief review to set up the notation and for the discussions. And then I will discuss the major part of today's presentation, the non-stationarity in terms of the time of day and diff-wake effects. And I'll discuss the model we've done and the estimator we proposed, and then addition analysis for the estimator in terms of a large sample properties, how to do valid statistical inference with our estimator in the scenarios with the non-stationarities. And I like to then conclude my presentation by discussing other type of non-stationarities and some related work on that. So a brief review of a standard A/B test is we think about users coming to a platform or a mobile phone app, and they may either use a mobile phone or a web to enter and join the platform. And standard A/B tests in that setting, in particular these online platforms, think about that as once the user arrives, there is a probability, maybe independent of other users, maybe not, but we're thinking in this standard setting about independently. So each user has independent probability to be assigned to control or treatment, and it's marked as A and B. A represents control, B represents as treatment. To put the discussions in a bit more context, we think about the control maybe as a user interface or as a particular design strategy that the platform is currently using. And the treatment is something new, a new design or a new strategy that the platform likes to examine. and usually has not been implemented, launched before. And of course, these percentages are also viable. Maybe it's 10% to 90, 80 to 20. It depends on different scenarios, but it's also a kind of parameter that we use in the later discussion. In terms of users, they're the kind of delicacies when it's applied in the platforms. Sometimes user refer to customers with particular ID, in the sense that if I'm a customer, the platform knows that it's me, and I get assigned with a probability to either control treatment. But sometimes users also refer to what they call a session. A session is not tracking customer ID, but more of whenever some user opens up the app, that means a session starts. And when the user, maybe after open the app, spend 5 minutes or 3 minutes on the platform, and then quits. So that duration of time is called a session. A follow-up of that standard A/B test setting. We're thinking about there is some specific metric that the test is interested in. Usually there are multiple metrics, revenue, costs, other welfares, but we're thinking about the setting where there is a unique metric. Maybe it's the expected revenue, let's say, generated by each session. We're talking about A/B tests where the test runs randomized experiments, given traffic of flows of users or sessions going into the experiment, put some of them randomly to the treatment, some of them to the control, and then as trying to answer the question, is the treatment significantly better than the control, or equivalently, is the average treatment effect positive? So the ATE, the average treatment effect, we're using the alpha in this presentation to denote that quantity. Well, it's of course unknown. It has some true value, but we'd like to estimate that quantity using the experiment data. And it's, for example, here, if the metric is set as expected revenue, is the expected revenue of treatment minus that of the control. Okay? And the standard A/B test procedure does kind of the following thing. They run experiments. Of the experiments, collect data, and with the data, do estimation and provide statistical inference. And here I'd like to highlight that this question is of equivalent importance compared to the estimation of the average treatment effect value, providing a central limit theorem, for example, and use that to construct confidence intervals and compute some p-value using the asymptotic distribution. Okay. And some notation I'd like to specify, and also to describe in terms of for A/B tests, what are the phases of run experiments and collect data they exactly do. Usually we think about the here there is a time horizon of here denoted by big T, and T, let's say here is 1 week or 3 weeks, and this time horizon, and then sessions mentioned briefly that in terms of can think about equivalent as users without tracking the ID. They arrive at the platform, at the experiments over this time horizon, and in the experiment phase for the ith user, it's assigned to the treatment with probability p, and let's say to the control with the rest of the probability. And of course, many A/B tests have more than one treatment, but we are using here as a single treatment versus control for the ease of description. So if it's assigned to treatment, we denote that this big I indicator of the ith user as 1, otherwise 0. And then for the ith user session, in the experiment, we get to collect the observed random outcome. For example, in those a few minutes session that the user maybe arrive on Monday morning, this outcome represents the revenue or maybe some other metrics, clicks that's collected during that the time that the user stays on the platform. And then after the time horizon 0 to capital T, the notion here is their experiment data obtained as it ended up with n samples and representing whether they assigned to treatment or control and their associated random outcome. And the estimator for the average treatment effect in the naive setting, naive doesn't mean it's it more mean that's simple. The standard it's essentially in the standard setting we take all the samples that are assigned to treatment, compute their average effect in terms of using their random outcome, and then subtract by the average sample average for the control. And for this naive simple estimator for the average treatment effect, by statistical inference, we really mean to evaluate the large sample distribution for this estimator, build a central limit theorem. Well, in the standard setting, when the data are independent, identically distributed, IID setting, these things are pretty straightforward, even though, of course, there are underlying theorem that guarantee those. And the purpose is to be able to construct asymptotically valid confidence intervals to make sure that whatever p-value or other inference metrics reported are valid. So there are two desired properties for an A/B test estimator to estimate the average treatment effect. Well, we term it in this presentation. One is accurate, meaning that we like this estimator to be unbiased or at least asymptotically unbiased. And we know that if it's not unbiased, if there's a bias, it's usually very difficult to know the exact quantity of the bias. So it could be ending up that the estimator has an expectation and the true compared to the true value of the average treatment effect, they may have different signs. That's a very undesirable situation. And the other property referred to as efficient, meaning that we like the estimator's variance to be, of course, given the first property, right? Otherwise, we can always set the estimator to be, let's say, constant. But we like the variance to be small, to have low variance. And part of the benefits of having a estimator that has low variance, it means usually that the confidence interval is narrower. It's more there's more confidence in terms of claiming that is above or below some threshold, and these also implicitly translate to a shorter amount of time that's needed to conclude an experiment. But the point on this page is also to note that for the naive estimator, the very standard estimator to estimate the average treatment effect, it works well in terms of both criteria, accuracy and efficiency, if the data collected are independent and identically distributed. However, one point of this presentation is that that if the data are not identically distributed, well, of course, there can be different ways of causing this not identically distributed situation. But in particular, if it's caused by non-stationarities. For the naive estimator, neither of these properties will be guaranteed to hold. Okay. And by non-stationarities, I like to use this illustrated plot to show the type of non-stationarity in terms of time of day and day-of-week effect. And this is plotted. If you look at the solid lines on the top, this is about one particular metric, and one color of the line is treatment, T, and the other color of the line is control, C. And the x horizontal is here. Axis is the time of day and day of week. And we see that both the treatment and the control in terms of their effect depends on the time. And also, even though it's not explicitly plotting their difference, the T minus C, but we can see from this that this plot that if we subtract T and C at the same time, the difference is also changing with time. But this is the type of non-stationarity this part of the presentation is concerning with, and the different reasons that cause these type of non-stationarity. But one thing, for example, we can think about is let's see if it's a platform where people do shopping, then even for the same customer, opening the app on Monday morning and Saturday evening may cause different patterns and behaviors, and during the working hours and off working hours, it may also be different. But this, of course, extends to some other entertainment apps, some news apps. If we open that up during working hours, maybe just for a brief review, but there may be lengthy reviews and more activities during off work hours. But there are different reasons for non-stationarities in terms of these time of day, day of week effects. But this is what we refer to in terms of non-stationarity. And it's kind of so this on this page is also outlining a bit of what we're going to do next. One is ignoring these non-stationarities, meaning that if we presume that we don't care about those non-stationarities, I just collect the data and do the standard A/B test, naive estimator. If we proceed with that, there will be lower estimator efficiency, and also it causes the estimator to has a bias, and this is partly also aligned with the Simpson's paradox. In particular, if the treatment assignment probability, the proportion of the users assigned to treatment control, if they have changed with time and not properly considered. But these are some potential issues by ignoring the non-stationarity in A/B tests. And in terms of to handle these non-stationarities in the form of time of day and day of week effect, we are developing a non-parametric continuous time stochastic model. It's more to facilitate the definition of data generation processes, and we propose some estimators and also establish a central limit theorem. And a small heads up there is that when it's in a non-stationary world, establishing a central limit theorem really requires also to specify some limiting regime, and by sending something to infinity, and what that really means, be more specific when it comes to those pages. There's some here's some partial list of literature, even though they are put in the in the category of experiment design bandit. Some of these works really cover more than one area, sub-areas, topics, but our work here is different from the experiment design and bandit literature, in the sense that these literature usually focus on how to adaptively or non-adaptively specify what probability, what proportion of users are assigned to treatment or control or different treatments. In our work, we are focused on the estimation side of it, in the sense that the data are already collected from the experiment, and our task starts from the moment that the data are collected. But we're not touching the phase where how the data are generated. We're not controlling the experiment designing process. Okay, that's and our work is closely related to the existing estimation of A/B tests, and closely connected to the simulation literature, in particular the post-stratification method that we're using and developing our estimator based on post-replication and making some moderate changes compared to the classical post-replication method. But this is a partial list of literature related to our work. So I'd like to proceed into the stochastic model in terms of continuous time that specify for our estimation task. And as briefly mentioned, our job in this estimator and inference method starts from once the data are collected, right? So these data from the experiments, after running these experiments in the time range of 0 to capital T, these data collected. Again, this I represents the ith customer, ith user. This II equals 1 or 0 represents whether it's being assigned to treatment or control. Yi is the observed outcome. The Pi here is when the customer arrives or starts. Maybe it's the Monday 9:56 a.m. some timestamp that's collected. So these are the data. We are not again, we are thinking about estimation and inference task. We're not thinking about, okay, after this time horizon, do we run more experiments, or within the time horizon, how do we change the assignment probability? We're not talking about those aspects, but only on the estimation side of the job. And the model in terms of non-stationarity, in terms of the random outcome, so we're thinking about, okay, if a user starts at time t, let's say Monday morning at some specific time, we're presuming the model as the random outcome has the mean mu1 t, standard deviation sigma 1 t, and also a noise here. We're presuming it's mean 0, variance 1. We have some slight more assumptions for the variance in terms of having a little more than a second moment existence for the proof of central limit theorem. But here we're not presuming that to have a specific distribution form. And if it's a treatment assigned to treatment, it follows this model. If it's assigned to control, it follows this Y0T model. Again, this is the mean effect. Of course, this mu1, mu0 are not known. Sigma 1, sigma 0 are not known, but these are presuming to be the underlying stochastic model in terms of the random outcomes. Okay. And so we need some more discussions in terms of data generation process, different from the independent identically distributed setting. In that setting, the data generation process is fairly straightforward to describe because every data additionally obtained every data point is just identically copy distribution wise and independent. Very straightforward to specify. But in the non-stationary setting, there's kind of a timeline there. It's difficult to say that, okay, after running experiment for 2 weeks, okay, I like to say, okay, I need to go back and obtain one more sample on last Tuesday's morning. Okay, that's not quite feasible. That also partly suggests the need to describe in more details about the data generation processes. And here, for example, we need to describe the customer arrival process or user arrival process. Here, let's say we presume it's a non-homogeneous Poisson process with a time-varying arrival rate function. Essentially, the process really doesn't need to be Poisson, but can be extended to other models. But it's more to denote the time dependency in terms of how frequent the customers, users arrive at different time of the day. And there are a few parameters also I need to use in future slides. One is this lambda bar. So lambda bar represents for this stochastic process running the experiments between 0 and capital T, how many users, right, will be entering the experiment collected during the experiment horizon. And this is the aggregate arrival rate. And also this FT represents a normalized arrival rate where think about this more of a density function that represents how likely that a user starts at a particular time of the week compared to other time of the week. And one thing to note that is really here in this non-stationary setting, the sample size is viewed as a realization of the random variable that denotes the total number of users arriving in the time horizon. So part of this is we think is when we specify the experiments in these settings, we specify, okay, we're running the experiment for 1 week, for 2 weeks. Instead of saying, okay, we're aiming to collect 10,000 data points, setting n equals to 10,000, it's usually not like that because for 10,000 users, maybe you run experiment after 2.5 days, you already collect those number of samples. But rather it's by specifying, let's say, a week, some time horizon, and whatever the sample size ends up being. Okay? B. So that's the data generation process on the user arrival process. Again, this the need is to discuss this data generation process is because of the non-stationarity, right? If everything is stationary, customers really user behavior really doesn't change over time, does not depend on time of day. Then it goes back to the independent identically distributed setting. It would be easier. There are also another source of element in the data generation process in terms of the so-called treatment assignment probability. So it's PT denotes the probability of assigning user a session to treatment if they arrive at time t. Okay? So for some scenarios, this PT are just constant over the entire time horizon. But for other scenarios, these treatment assignment probability may be time varying. For example, in a class of experiments, the treatment is something new, right? A new strategy that never been tested online. so people tend to start with, let's say, a small fraction of the user traffic assigned to treatment, maybe starting from 1% of the traffic, 3% of the traffic to treatment. Part of the consideration is that we don't know, maybe there's some really issues with the new treatment. Maybe it causes delay, other things. They like to start with a small proportion and then gradually move that up. So that's part of the reason causing PT to be time varying. And the third item here denotes PT can also be time varying if maybe some adaptive tools, maybe some learning algorithms, some other bandit algorithms are used to dynamically adjust these PT, right? Where in this case, PT would depend on the random outcomes observed from the previous time slots. So listing here, not to suggest we're controlling PT, but more of we need to model how the data generated, and part of the process is that how PT has been selected, and we're trying to make our assumptions as general as possible, in the sense that not limiting, giving too much limitation in terms of how the PT are selected. So these are the data generation processes, and the estimation task is to use the collected data to provide an estimator for this alpha. And mu1 minus mu0 can be viewed as the difference between the effect of treatment and control conditional on time t. And then it's weighted by ft, this is the customer arrival rate, normalized version of that. So this is really the unknown quantity alpha that we like to estimate. And here in the middle of this slide, putting on the naive estimator. And in terms of the expectation of that, and to really illustrate that this expectation of a naive estimator is not necessarily equal to alpha. Okay? And in particular, we can note here, if PT is changing with time, it's certainly cause a significant difference between these two quantities. Okay? So next, I'd like to discuss our proposed estimator based on post-replication and associated large sample behavior inference on the relevant discussions for the proposed estimator. The post-stratification idea, to my knowledge, started from many years ago, widely used, for example, in the polling side, and it's widely used in Monte Carlo simulation to construct estimator. The purpose there is mainly to reduce variance, and in particular, conventionally we think about in this non-stationary setting that we specify the time, let's say group the data into a day of the week, Monday, Tuesday, 7 days, and compute the effect between treatment and control difference for each day, and then do a weighted sum of those based on the number of samples. So that's the rough idea of post-replication. So there are two things that are slightly different in this non-stationary setting for the A/B test. One is we're also using the post-replication to model more granular levels. So here in the third item, if you think about doing the stratification level to be each day of week, but on Monday they're Monday morning and afternoon, Monday evening, they may also be different. But we might need to do more stratification levels even within Monday. But how granular, right? Do we go to every hour? There is stratification level every 30 minutes or every 5 seconds. There sort of need some hopefully guidelines in terms of how granular we like the stratification levels to be. So we are kind of just using this term sample-based post-stratification SPS estimator, or to really indicate that the number of the stratification levels depends on the total amounts of samples, in the sense that we like many stratification levels, a big number to make sure that it's a high granularity thing. It's taking consideration into granular time of day effects, but also we hope each stratification level to contain a sufficient number of samples, right? If we put the stratification level, each level as 1 millisecond, it doesn't maybe contain even one sample, but we need the length of each small time interval as the strata, to contain a considerable amount of samples, right? So the number of stratification levels depend on the samples, and also how long each stratification level is can also depend on the sample. But here on this page, we are describing a simple illustration where each stratification level is, in terms of the time length, is equally divided. Right? We can think about this as, given the total sample size n we collected, we put small kn as the number of stratas, and then we divide the time horizon equally, and on each of the stratification level, we do the sample average within that, the difference of that within the stratification level, and do the weighted average. So this is the standard post-stratification estimator, but we note that the Kn can depend on the sample size, but also the length of each stratification level can also depend on the sample size. So for the estimator that was proposed, we need to evaluate the large sample distribution of central limit theorem for the proposed estimator, so that we can safely write down the confidence intervals. And here there's question about, we need a appropriate limiting regime. So in the IID setting, independent identically distributed setting, the limiting regime, and actually most times we didn't specify the limiting regime, but mostly because I think it's straightforward what it means by sending something to infinity in the IID setting. You consider a sequence of experiments, let's say identified, indexed by the label n, the sample size, right? So n represents the number of samples, and we're sending the n to infinity. That's in the IID setting. But in the non-stationary setting, sending n to infinity, the sample size to infinity, needs more specification, because if you send n to be a larger value, the additional data we obtained may have different distributions, right, compared to the first n samples. So we need to be careful, at least in terms of describing sending the sample size to infinity. But also, briefly mention this, in the experiment setting, usually it's more about setting the time horizon ahead of time, to be a few days, a week, a few weeks, depending on the context. It's not usually setting, collecting 10,000 samples, right? And then there's a question of, well, t is the time horizon, the length of that. Are we sending the capital T to infinity? well, sometimes it makes good sense, but in the A/B test setting, if you're thinking about okay, the horizon is about 2 weeks, 3 weeks, t itself is not usually going to infinity. So we really need to specify a limiting regime. Of course, this is not a unique. It's not that there is a unique choice of limiting regime, but we need some limiting regime to put the particular data generated in that regime in order to make a valid claim of a central limit theorem. Okay. And what we do briefly here in terms of limiting regime is about thinking about the data generation process, not sending the sample size to infinity, not sending the time horizon to infinity, but sending the arrival rate, aggregated arrival rate, lambda bar to infinity. We can think about that as in terms of the arrival process, that it's given the time horizon, given the normalized arrival rate, but sending the intensity, the aggregated intensity of customers that arrive in that time horizon to infinity. And of course, each value of this lambda bar corresponds to an entire data generation process for the A/B test experiments. And the regime is specified by sending this lambda bar to infinity. Okay. This type of limiting regime makes think some good sense when platforms is filled in with a large number of users within the magnitude of weeks and days. But this is the limiting regime that we specify. And with this limiting regime in hand, we are able to build a central limit theorem under the assumption. So there are some regularity assumptions in terms of specifying like the dependence of the effect for treatment or control on time needs to be piecewise continuous, assumption like those. And we need the number of stratification levels, Kn, depending on n, need to satisfy that if the sample size ended up being very large, the number of stratification levels end up to be also infinity, but also it's a small order of square root of n, meaning that on average, each stratification level at least contains square root n magnitude of samples. Okay? And we see that there is a central limit theorem built for the estimator, and symptotically it's unbiased on the square root level, and it has this asymptotic variance specified by this term. Okay? And see, it depends on the this expectation of the effect, and also the standard deviation that may also depend on time. I think because of the kind of the time, I'd like to just briefly mention that in terms of the proof, it's starting from the setting where these PTs, treatment assignment probability, being a constant, then extended to the scenarios where it's piecewise constant, and in the end, to situations where these PTs are can depend on the previous data. And then there are these controls of the terms, and with the goal of, in the end, using the standard Lindeberg central limit theorem to build up the major parts of the terms, and to show that the other terms has a smaller order of errors, which can be ignored on the central limit theorem scale. And on this page, it basically says that, okay, we have the central limit theorem, but we sometimes want a specific notion of how to construct confidence intervals. So we provide a procedure of constructing confidence intervals where the sample variance is estimated by only based on data. So basically, given the data set obtained from the experiment over the time horizon, we get the data, we plug in this formula, to get the estimator of this variance, and also the estimator based on the stratification idea. And then this is the confidence interval, right? So the procedure is more or less completed in this sense. And also because of the central limit theorem we discussed, it guarantees the asymptotic validity of this the proposed estimate. So this page describes that the estimator we proposed based on the post-replication sample-based post-replication, where the stratification level depends on the data, is for some sense best achievable. And in terms of the asymptotic variance that appears in the central limit theorem level, and again, for the basically says that, okay, given the collected data over the time horizon, if using that to construct the estimator for the average hidden effect, for any regular estimator, asymptotically unbiased, constructed based on the data, the similar variance is cannot be better or smaller than this V optimal. And it turns out that V optimal is exactly the asymptotic variance that achieved by our proposed estimator. Okay. So this is a sort of a guarantee to answer the question, can the estimator do better in terms of some notion, and the notion here is in terms of asymptotic variance. So we have shown that this estimator is asymptotically unbiased, enjoys the asymptotic variance, enjoys the central limit theorem. We use the next page to briefly discuss in terms of it was shown to achieve asymptotically no bias, but in terms of variance reduction, how much exactly the variance reduction does compared to naive estimator. We provide a quantitative analysis considering the case where PT is set as constant. So if it's PT is set constant, this is the term of the optimal asymptotic variance, also achieved by the sample-based post-replication estimator. This term is the naive estimator's variance, and tau here represents, we think about this as it's kind of a term used here to make the formula more concise, where tau denotes a random time of arbitrarily chosen user, that user's arrival time. Okay? We see that the optimal variance and naive variance, they share the same second part, where of course these parts, you see that the uncertainties in the random outcome, and they are just embedded in the observation, cannot be eliminated. But in the first term, first part, the two terms are different, and we know that the variance in the above term formula is smaller than the bottom one. But if you think about how much, sometimes the difference is small, sometimes difference is larger, but the reduction of variance is more significant when mu1t and mu0t. Mu1t again is how the treatment performance depends on time. Mu0t how the control performance depends on time. If they have closer patterns of moving toward the same direction, then the reduction is more significant. And it sort of corresponds to the illustration we have kind of shown that these treatment control, their dependence on time, go along kind of in similar direction with time. Okay? So that's in terms of the discussion in how we handle the time of day effects and day of week effects. I'd like to conclude with a few more pages by noting the following observation. So even though we have considered the time of day and day of week effects, sort of claim to handle in a proper way of those, but we are more or less presuming in considering the time of day, day of week effects by implicitly assuming that these patterns are going to repeat themselves over weeks, right? Well, it's a related notion is that usually, for a given experiment we had run on this time horizon, maybe 1 week, maybe 3 weeks, a proposed estimator, but they are more or less presuming that this pattern is going to continue in future, right? Sometimes that's the case, but sometimes that's not the case. And this plot as an illustration, I could see that this is for a time span of 2 weeks. Okay, 2 weeks, and there's 14 days here, and we see that if we only look at the first week, there's a pattern, but their day of week, time of day pattern. But the second week, well, there's some similarity to the first week, but it also has its own non-stationary pattern different from the first week. So this more or less kind of breaks the implicit assumption that things are stable from week to week. So this is something we are working on. Also, we note the limitation of these things in the sense that, well, if we think about this situation one where let's say we run experiments for 1 week and we estimate the average treatment effect, and if it's estimated to be significantly positive, then usually the treatment, let's say, is called a success, and then fully launched, meaning that from the afterwards, all the user traffic is assigned to treatment. This is aligned with the notion that things may be different even from week to week. It's also indicates that, well, if a treatment is claimed to be better during the experiment horizon, how confident we should be in terms of assuming their future performance, right? We definitely implicitly have some continuity assumptions when launching these treatments by presuming that, okay, this treatment has performed better in the past 3 weeks. It's anticipated to also perform better in the next 3 weeks, maybe 3 months. But for how long, right? And do we need to monitor that? This relates to the discussion of thinking about the midterm or longer term effect of the treatment related to that literature. But there's also another situation in terms of different non-stationarity I'd like to briefly discuss in this presentation that, well, if the treatment is and maybe a newly designed algorithm, and it itself is dynamic learning and evolving before it's implemented. I mean, it hasn't seen enough relevant data before, but the treatment is something new. And if you estimate the average treatment effect on the horizon to be significantly negative, right? Indicating that the treatment is bad. shall we just call it a stop and failure and discard the treatment? Well, sometimes yes, sometimes not. Showing the following plot, you see that okay, this is a treatment. Well, the plot plots the relative difference of the effect of treatment versus control. We see that it's all negative, right? And these are the plotted in terms of the first 7 weeks that the treatment is being examined. And if we think about just running experiments and do the A/B test, okay, for this 7 weeks, we see that the average effect, it's about 10%, 8% worse for the treatment. So maybe it's by standard notion, not considering the non-stationarity, it's a failure, but we see that it's dynamically changing, right? It appears that the treatment is kind of getting better over time. So maybe a different thought is, okay, for this type of non-stationarity, it's from week to week, things are dynamically changing. Maybe the conclusion for some of these scenarios is not to call it a failure, or maybe give it more time to let the treatment perform itself. So we have an ongoing work related to this notion. Okay. But this is my last page, and I'd like to conclude here. Thank you.
Thank you, Zeyu, for the nice talk. I think we have time for some questions.
So it's kind of nice that you're able to use stratified sampling here to stratified sampling ideas, sorry, to sort of dig in here. Is there any value in knowing the arrival rate process, the arrival rate function of the Poisson process?
Yes, there's value of that. Good to see you here, Shen. Thanks for the question. I think knowing the arrival rate is actually important. And it's not discussed in this presentation, but knowing that as additional level of variance reduction, in the sense that maybe on the platform only 2% of the entire traffic are assigned to this particular experiment. Of the 2% traffic, 1% to treatment, 1% to control. But but knowing the overall arrival rate, even not directed to the experiment, that information is useful. I think it's more or less analogous to doing this polling, right? So this presentation only talks about, okay, we have done 30,000 samples. We're just using that to do post-replication. But if you know the entire populations, that more information in terms of how the population is composed of, I think it appears analogous to the point that you raised. And yes, I think it offers additional. Knowing the arrival rate offers additional level of variance reduction. Yes.
Got it. Thank you.
I have one question. So I'm trying to relate your settings to non-stationary bandit. And usually there they have a so-called notion of kind of like measuring the level of non-stationarity throughout, let's say, in the time interval of t time step. And that's why usually the regrets or kind of performance guarantee will depend on the magnitude or kind of like the level of non-stationarity of the problem. So intuitively, the more change you experience during the time interval, the more difficult to learn. So I was wondering, is there a similar notion or similar measure showing up in your problem here?
Yeah, Xiaoming, thanks for the question. That's a kind of a very insightful one in the sense that in the bandit setting, among the different ways of defining non-stationarity, there is this one you mentioned that regulating how much fluctuation overall or within some horizon that the changes can be, and under those changes, they consider they definitely can allow some jumps, right, between even between adjacent time period, and I think one difference here is in most bandit setting, it's first of all, of course, this work is different from the bandit work in the sense that it's only concerned estimation. But bandit usually model in the in discrete time horizon, right? The time period 1, 2, 3, 4. It's and the definition of there. And here, in kind of a continuous time horizon, and we try to model how these changes happen with time. So we need kind of difference here is that we need some sort of continuity. It does not need to be always continuous over the time horizon, but it needs to be kind of at least piecewise continuous. And in the end, kind of the work on the theory part is utilizing that if it's continuous, then within a small time horizon, the effect are similar. So that's but I think in the bandit setting, in the discrete setting, they're more flexible in terms of there's no kind of this continuity notion, but their continuity is more of caused by, as you was pointed out, that there's overall budget of changes, and that more or less regulates the continuity in the discrete setting.
Thank you. Okay, if there are no more questions, then maybe we can stop here. Thank you again, Joey, for the really nice talk.
Okay, thank you, Qiaoming. Thank you, everyone. Bye.